Hi guys, welcome to today's level 2 chemistry tutorial. I'm just gonna make sure everything's okay. Alright, now just a reminder that you don't have to stay until the end of the stream, okay? Because the VOD will be up on the YouTube channel, so you'll be okay if you have to go to sleep. But I'm pretty sure no one has any exam tomorrow, so I deliberately waited until your English is finished. I don't want to do a stream just before your chem exam because you have chem exam in the morning, I believe, and I do believe that you do need to rest and sleep and just let it all go the night before and just be relaxed. Otherwise you might stress yourself out, and that might impact how you perform on the day. So how are we going to go through this? I've covered the 2018 and 2019 examinations, and I will just go through the concepts today. So I'll just speed run all the 3 topics, and I will go through some important concepts, and so yeah, so let's get started. So the first quick, I'll just go in the order of the topic. So we'll start with structure and bonding. So it's 5 critical external, and you can pretty much break this section down to 3 big questions. So you got Lewis diagrams, shapes and polarity. You got solids, which is probably the most boring part of the entire chemistry course, and then you have the enthalpy change, which is just calculations and explanations. Okay, so let's get started with some Lewis diagrams, shapes and polarity. So I got some examples here. I'll go through them one at a time. So for CO2, it's really important that you do break down, if you're not familiar with my method of doing this, just make sure you have a periodic table handy. So for CO2, to draw the Lewis diagram, and if you know the basic rules of organic chemistry, you don't have to use this method, but it works all the time for year 12. Okay, so these are the elements inside CO2, 1 carbons and 2 oxygens. So you have the carbon has 4 valence electrons, oxygen has 6, the oxygen also has 6. This carbon needs needs 8 to have a full shell, 8 and 8, and therefore you got 24 altogether, but you only have 16. So that means 24 minus 16 is going to give you 8 electrons, 8 bonding electrons. So that's going to be 4 pairs of electrons. So that's 4 let's not use the word pairs, this is 4 bonds. So that what that means is that for your for your CO2 Lewis diagram, you need to put 4 bonds between the two, between the O's and C's, and then you have to make sure that every single atom has got 8 electrons. So these two, the oxygen, each of them has 4 valence electrons, because if you look at that, that's 2 there, 4 there, and that's 8. So that oxygen is stable, that oxygen is stable. Now this carbon already is stable because it has 4 bonds already. So this is CO2. If I get rid of all the other noise, so this is CO2. What shape is it? You look at the central atom. So the carbon has only got 1 and 2 electron density around it. So this is 2 electron densities, all of them are bonded, therefore this has a linear shape, and the shape has a bond angle of 180 degrees. And so this is pretty much just achieved and merit stuff, right? But when you looking at polarity is you need to discuss 2 things. Okay, polarity, you need to talk about the dipole formation. So what the heck are dipoles? Because a lot of people just talk about, the shape is linear, therefore the dipoles cancel each other out, but you didn't even tell us what the dipoles are. So you need to discuss that, and then you need to talk about the shape. Okay, so the dipole formation is to do, you can look at my other videos, but I'm just gonna verbally explain it here, because we're running short on time. So the dipole is to do with uneven sharing of electrons between the carbon and the oxygen atom due to the significant electron negativity difference. So that means the oxygen in this case is going to be more electronegative compared to the carbon, and therefore you have dipoles. Dipoles means 2 poles. So think of the word pole. Pole, like this, you have the south pole, the north pole, they are oppositely charged. So di is 2, so that means you got 2 poles. So 2 poles just means you have a negative end, you have a positive end. So that's what dipole means. All right, and so the word dipole just means you have these slightly negative and slightly positive charges at the different ends of the molecule, and that results in the polarity. But in this case, if we look at the bond, the one end is slightly negative, one end is slightly positive due to the significant electronegativity difference between the atoms involved. They don't share the electrons perfectly, and they create bond dipoles. All right, and because this has a linear shape, overall the dipoles cancel each other out, hence CO2 is linear. Now, just for some tips and tricks, like just remember your carbon, most of the carbons, 99% of the time, bond 4 times. Okay, so they have 4 bonds. Your oxygen normally has 2 bonds, your hydrogen normally has 1 bond, your chlorines and fluorines and everything, and your what else, bromines, all of these bond once, and your nitrogen bond 3 times. And if you follow that rule, then you should be okay. All right, now let's move on to CH2Cl2. Now CH2Cl2, so I won't explain it as detailed as I did because it's pretty straightforward. CH2Cl2, so if I just draw the Lewis diagram, the hydrogen bond once, the chlorines bond once, and someone asks you, are there any exceptions in year 12? No, there are no exceptions. When you do year 13, then there might be some exceptions, but not in year 12. So CH2Cl2, so these are the this is a Lewis diagram. I can kind of follow the rule here. You can see hydrogen only bond once, the chlorine only bond once, so you just single bond everything. The carbon in the middle has got 8 electrons around it, 4 bonds, so everything's happy. And we make sure that each of the chlorines have got 8 electrons, and then hydrogen got 2 electrons around them, which is a bond. Okay, so this has a tetrahedral shape, but then this tetrahedral shape, overall, this molecule is going to be polar overall because you have 2 types of bonds. You have CCl bond and you have CH bonds. Okay, so that means you have two different types of bond dipoles. 2 different type of bond dipoles, and they can't cancel each other out. You can almost think of it as this is incorrect to think of it this way because it's 2-dimensional. If you think of something like, say, if I draw this 3-dimensional structure, if I do it like that, then you have one going into the page, one coming out of the page. It doesn't really matter how you think of it. These, like, say, imagine these 2 chlorines are pulling the carbon upwards and to the right, whereas the hydrogens are being pulled towards the carbon. Obviously, they can't cancel each other out. Okay, so the overall molecule is going to be polar because you have 2 different types of bond dipoles and they don't cancel each other out. Okay, so let's look at the other lots. I think I'm going to use some of the space up here. SO3, if you do SO3, this is a little bit confusing if you don't use this particular method. So each of these are group 16 elements, so they all have 6 valence electrons, but they all need 8 to be stable. So 4 8 is 32, 4 6 is 24, so you have 8. So 32 minus 24 is going to be 8 bonding electrons, and that's going to be 4 bonds. Okay, so your sulfur, 1 over here, 1 over here, 1 over here, you need to draw 4 lines before between the sulfurs and oxygen. Okay, so you go 1 2 3 4, and that's how you determine SO3. And then you have to make sure each oxygen has 8 electrons around them. That's why the top oxygen has 4 valence electrons, 2 lone pairs electrons, whereas the other oxygen have 3 lone pairs electrons to make up 8. So that SO3 has a trigonal planar shape, and due to the double bond actually distort this a little bit, so this is going to be slightly polar as well due to the distortion of the double bond. because the double bond is more electron, you have more electrons over there, so the repulsion is going to be a little bit different. You normally don't get SO3 in terms of polarity, because it's actually quite a little bit beyond the year 12 syllabus. Now BF3, this is something you do need to remember. In year 12 there are some exceptions for the, when we use this method of BF3. Remember that boron has electron arrangement of 2 and 2, 2, 2. Let's see. So this needs 7, 7, 7. Boron actually needs needs to have 6 electrons in order to have a full outer shell. So just remember your boron only needs 6 to have to complete the shell, because it doesn't have enough protons to hold on to 8 electrons. Okay, so that's going to give you 3, 8, 20, 24. So that's going to be 30. 21. That's going to be 3, 1. Wait, did I mark it up? 2, 3. Sorry. Boron's 3. My bad. So that's going to be 24. So 30 minus 24 is going to give us 6 electrons, so 3 bonds. So BF3 is going to look like this. Okay, so BF3, again, there are, in this case, because the boron only needs to have 6 valence electrons, 6 electrons to have a full outer shell, so you don't need to do that lone pair of electrons. If you do that, then it's wrong. And if you look at this boron, this has a trigonal planar shape, because you have 1 lot, 2 lots, 3 lots, 3 regions of electron density around the boron. All of them are bonded, so you have a trigonal planar shape. And because you still have the dipoles, you still have the bond dipoles of boron and fluorine. Like these two elements have significant difference in the electronegativity. So what that means is that they would want to, like the fluorine, want the bonding electrons closer to itself, and the boron's like, yeah, I don't really care that much. You can sort of have it your way. So that's uneven sharing. So that create bond dipoles, but then these 3 bond dipoles will cancel each other out perfectly due to the symmetrical shape. Okay. So you can find lots of videos on the polarity stuff that I've done in previous exams, but that's just a reminder. And that goes all the way up to nexons. The bond angle stuff, that's you tend to have, like, if you use a study guide, there's a page in there that has got all the bond angles. And just to keep it simple, if you have got, let's say, 4 regions of electron density, the bond angle is always going to be 109.5 degrees. Okay, give or take. I mean, the more chemistry you learn, the more that you understand that it's actually not going to be 109.5 all the time. Now, if you have 3 regions electron density, the bond angle is always going to be 120. And if you have 2 regions electron density, the bond angle is always going to be 180. So let me give you an example. Like, say, for example, water. What is the bond angle of water? Water looks like this. So what shape is water? So if you look at the central atom, which is oxygen, this has 1, 2, 3, 4 regions of electron density. So it has 4 regions electron densities, and these 2 suckers are lone pairs electrons, so they cannot be seen. So this has what we call a tetrahedral arrangement. But because you can't see them, you can't see these 2 electrons, therefore you have a bent shape. And what is the bond angle? 109.5 degrees. Okay, so you can have different, like I can draw NH3, like ammonium. Ammonium looks like this. NH3, this also has 1, 2, 3, 4 regions electron density. So the bond angle is also going to be 109.5 degrees, because these electron densities want to repel each other as far away as possible. Okay, but because you can only see 3 of them, this has a trigonal pyramid shape. But again, it has a tetrahedral arrangement because you got 4 things around them. That's just a really easy way to memorize them. You don't need to go, what is the bond angle of a really unfamiliar shape? Just look at how many regions electron density you have. All right, next one, solids. So solids is going to be the part that you can pretty much rote learn. You can memorize lots of the things, but here's a table that you tend to see this quite often. Let's say, how do you distinguish what type of solids you have? Look on the periodic table, and then just below I think it's boron, you can draw a little staircase. Everything on the left hand side are metals, everything on the right hand side is non-metals. And then if you look at the solids, so if you look at aluminium, aluminium is on the left hand side, it's obviously a metal, and it's just sitting on its own. There's nothing else bonded to the aluminium, so this is a metallic solid. Okay, so, and then in this case, if you have Mg is sitting on the Mg sort of over here, chlorine is over here, so you have a metal and you have a non-metal bonding with each other, therefore you have ionic. And then sulfur is a non-metal. If you just have a non-metal hanging out on its own, then it's molecular. That's how you tend to remember it. And then you have the three examples of giant covalent network. Giant covalent network. Okay, so which is diamond, silicon dioxide, and graphite. Just memorize them. Okay, you do need to know these three, because most of the time people get silicon dioxide confused. They think it's molecular, but it's actually a giant covalent network. So what type of particle? This is made of metal atoms, this is made of ions, this is made of molecules. And the attractive force, this is metallic bonding. And the MgCl, this is ionic bonding. And this is intermolecular forces, which is the weakest out of them all. Okay, intermolecular forces. Okay, now the physical properties. So what you need to be able to do is to compare difference in the physical properties using the bonding to explain. Like say, for example, why does, like say, aluminium has such a high melting point compared to the sulfur? And when you explain it, you just say, well, aluminium is a metallic solid. It's made of metallic bonding, which is the delocalized electrons bonding to the nuclei, which is really strong. Therefore, you require lots of heat to break that apart, compared to sulfur, which is held together by weak intermolecular forces, which doesn't require a lot of energy to do that. Hence, you have a really low boiling point or melting point. And electrical conductivity just depends on the melting point and boiling point. You need to compare the strength of the bonds, of the force of attraction, sorry, not the bond, the force of attraction. And when you talk about electrical conductivity, you're looking for free moving electrons and ions, one of the two. So I'm going to highlight all the things that can conduct electricity here, which is aluminium that can conduct electricity, graphite can conduct electricity, and MgCl2, when it is dissolved or aqueous or molten, then it can conduct electricity. Why can aluminium conduct electricity? Because aluminium has the structure like this. You have free delocalized electrons that just randomly move around the structure, and that allows it to conduct electricity. Graphite is made of rings. Like say, if you are writing things down on pieces of paper, like say in a book or something, just imagine that one layer of graphite is one piece of paper, and then underneath that piece of paper you have another piece of paper, and that's another layer of graphite. So you just have these because each carbon bonds with 3 other carbons for graphite, and they form those hexagonal rings, and the rings, the layers of rings are stacked on top of each other, and between the layers you have long pairs of electrons that can conduct electricity. Okay, now MgCl2, this is normally a really common question. Like say the ions are kind of bonded like this, the positive are bonded with the negative, and then the negative are interacting with the positives. Okay, so it's kind of like a 3-dimensional structure. Now, if it's a solid, it's not going to conduct electricity because all the ions are not free moving. They're locked in that 3-dimensional structure. But if it's molten, that means melted, or is dissolved, so that becomes aqueous, they can conduct electricity. Okay, so solubility is compare the strength of the interaction before and after. Like say, why doesn't aluminium dissolve in water? Like, so let's just use that example. Again, this is covered in the old exam paper, so if you want to have a look at those videos. So for aluminium in water, why doesn't that dissolve? That's because the aluminium hanging out with the aluminium is stronger than aluminium hanging out with water. So what that means is that the aluminium does not want to hang out with water. It is held together by metallic bonding. They really like each other. They like, oh, what are you, H2O? You're not as cool as we are. I don't want to hang out with you. Get it, get out. So it doesn't. So H2O can't get into the solids and interact with the aluminium, so it just stays out and it doesn't dissolve. Okay, so very straightforward stuff, I hope. And why does something like say if I have NaCl, why does that dissolve? Because the water molecules, you would have seen this diagram before. Sorry, it may sound I'm rushing a bit because I'm trying to do 3 standards in 1 hour and a half. So the oxygen of the water is slightly negative, and then the hydrogen is slightly positive. And what happens, like say when NaCl comes into water, the Na pluses get pulled apart by the water molecules as well as the Cl minuses, because all the positive ends of the water molecule will start facing, they're like, hey, you're really positive, because this Na plus is much more positive than the slightly positive of the hydrogens. So the Na plus gets pulled apart, and then the Cl minuses, as you can imagine, also get pulled apart and get surrounded by the water as well. And this, so the interaction that we have on the right hand side is stronger than the previous arrangement, hence they dissolve. Okay, and malleability is just the ability to change shape. Like say, if you look at this ionic solids, if I apply a physical force down this way, I'm going to push all the positive ions next to positive ions, negative ions to negative ions, and the whole thing shatters. But if I apply a physical force to this metallic solids, it's not going to do anything, because, well, it's going to not going to break the structure. It's going to make it malleable, make it into different shapes, and that's when it's going to stay as a solid but change structure a little bit. Okay, so that's the solid stuff. It's really not that interesting, to be honest. It's my least favorite part of chemistry in level 2. So let's get on with some enthalpy. So these questions, I don't think you would have seen them. They're not from old exam papers or anything, so let's just go through them. Because I'm seeing the live chat being quite active. If you just here for Kim, if you want to concentrate, just turn live chat off. Because I'm just going to go through this really quickly. All right, so let's have a look. So circle the word that best describes enthalpy change. So we're going from liquid to solid. So going from liquid to solid, just remember, liquid is like this. The particles are kind of close to each other, but solids, the particles are really close to each other. So when you're going from this arrangement to that arrangement, you are kind of making bonds. So this is bonds making. You are going to have an endothermic reaction. Okay, and when we have this question like this, and how to explain it, just bonds making. You're going from liquids to solid. You are forcing the particles to stay together, and energy must be released. Okay, sorry, energy must be absorbed in order for this to happen. So the other way, if you go the other way, then that's going to be exothermic. So let's, oh, hold on. Did I just, this is why I don't do these at night times. Let me just, so bonds breaking, let's write this down. Bonds breaking, yeah, I got this other way around. Sorry guys. See, this is what happens when I do things beyond my bedtime. Bonds breaking is endothermic. Bonds making, apologies for that part, is exothermic. Okay, so in this case we are turning liquid to solid, so we are making bonds, so this is going to be exothermic. So apologies. You can always remember one as remember one and the other one's the opposite. I tend to remember bonds breaking is endothermic much more than I would remember the other one, because if you want to break chemical bonds, doesn't that make sense that you need to absorb energy to make it happen? So hence it's endothermic. Next one, this is a positive number. So straight away that's endothermic. Why is, and they ask you to explain why that is a positive number. Next one, so as you can see, the reactants, this is something, the reason why I show this is that this is something you need to be able to draw. Sometimes they ask you to draw things like these. So just get used to seeing something like that. So this is clearly an exothermic reaction because your product's enthalpy is less than your reactant's enthalpy. Okay, so when you want to draw an endothermic reaction, it's going to look like that. So just get used to seeing things like this. Now, calculations. So where's my calculator? Oops, excuse my background. Why is it not working? Oh, it doesn't want to be attached. It doesn't matter. So grab a calculator. Excuse my Man United background. That's a team I support. I'm trying to get a calculator to fit on OneNote, but it doesn't like it for some reason. So just because I was trying to show you the calculation part, does really not want to do it. No, it doesn't want to do it. It's fine. You can look at my screen. You can check out all the games I have on desktop. All right, so let's just do this calculation. Just have a calculator on you because I was going to do the calculation on a emulator, but it's not going together, so let's just ignore that. Let's just do the calculation. So calculate the heat energy, 2.28 grams of magnesium burned in oxygen. So one is asking a question like this. Just highlight the element of interest, which is magnesium, which is this one. We need the enthalpy. I don't really care too much about the oxygen or the MgO. Okay, so first thing first, just look at this. Yeah, 2 magnesium is negative 2000 kilojoules. 2 moles of magnesium. So doesn't that make sense that 1 mole of magnesium will release negative 600 kilojoules of energy? That should be quite straightforward. I mean, that's just 1200 divided by 2. You shouldn't need a calculator for that. But why would I need to do this? Is that I know how many kilojoules would be released if I had 1 mole of magnesium. So how many grams of magnesium I have? So just remember, N equals small m divided by big M. Now the thing with the calculations, guys, if you do one step of calculation, you get achieved. So if you have no idea how to do these, just do the grams to moles calculation. Just do that first. So N equals 2.28. What is the molar mass? 24.3 divided by 24.3, and I'm just going to crunch these numbers on my calculator. 2.28 divided by 24.3, which is 0.0938 mole. Now, if you are doing the calculation with me, that's not the entire number that's being displayed on my calculator. I'm just rounding to 3SF, but on my calculator it actually says 0.09382716, which is going to be all the numbers that I'm going to be using for the calculation. All right, so let's look at this. So 1 mole of magnesium is negative 600. I have 0.0938 mole, so you just use 0.0938. Now, it doesn't matter if you don't include the negative sign, because I was explaining to quite a few people in the comment section before. The negative sign here, it just means energy is released. So when you're doing the quantitative calculation, you don't need the negative sign. You just need to remember that it is an exothermic reaction. Energy is being released. So when I'm doing this on my calculator, I'm just using the whole number and multiply it by 600, which gives me 56.3 kilojoules. And that's going to be my final answer. Okay, so this is rounded to 3 significant figures. So hopefully that's okay with you. So that's again, if you do struggle with the calculation part, don't leave it blank. Don't ever leave it blank. At least calculate the moles, because that will get you something. Okay, or even show this part. You might get something. You know, just. You never know. If you leave anything blank, you're definitely not going to get anything. So just, try your luck. Write something down. Don't leave a question blank. Now, calculate the amount of MgO produced if 10,000 kilojoules energy is released. Okay, so let's have a look at this. So in this case, we are interested in MgO. So same thing. Before I even look at the question, let me just think about this. 2 moles of MgO is negative 1200. That means 1 mole of MgO is going to be half of that, which is going to be negative 600. So 1 mole of MgO releases 600 kilojoules of energy. I've released 10,000 kilojoules of energy. How many moles would I have? So this is when you use 10,000, you use a kilojoules. I don't need to write K there. Use a kilojoules to divide by the per mole value. Okay, because this is the per mole value, I want to figure out how many moles I can actually get with 10,000. So 10,000 divided by 600, which is going to be 16.7 moles. Okay, so this is 16.7 moles, but normally when we ask you, let's not say amount, let's say mass. If we want you to calculate the mass, that means you need to convert the mole to, you need to convert this mole to mass. So that means N equals small m divided by big M, and small m equals N times big M. So that's going to be 16.7 times 40.3. Now remember, I'm using the entirety of the calculation in my previous answer, not just 16.7. And if I do that, that's going to be 672 grams, rounded to 3 significant figures. Okay. Next one. This is the bond enthalpy equation. So whenever you see whenever you see a table like this, this is a bond enthalpy equation. Okay, so you need to straight away just remember the change of enthalpy is the total of bonds breaking minus the total of bonds making. Oops. Okay, so what you need to do, oops, drop my calculator. Now what you want to do is that you want to I want to rewrite this into a Lewis, not the Lewis diagram, but at least a shape diagram. So CH3, so I want to show all the bonds. CH3, CH2. Now sometimes in NCEA, if they're nice enough, they give you the structure. And I really hope that they do, because that will save you a lot of time. Because if you can't draw these, then you're stuffed. Because you can never get it right if you can't draw these. 2 moles of CO2 plus 3 moles of H2O. Oops. And that's why you need to be able to do Lewis diagram. Because if you can do Lewis diagram, and this is organic, if you can do Lewis diagram and simple organic, you should be able to draw this without a problem. So what that means is that we need to break. So for bonds breaking, that means we need to break all of these bonds on the left hand side and add that up, and then break everything on the right hand side and add that up. Okay, and then take a difference, and that's going to be the change in enthalpy. So what do we need to break? Let me get rid of the highlighter so we can see. So what do we need to break? We need to break 1 CH bond, 2 CH bonds, 3 CH bonds, 4 CH bonds, 5 CH bonds. So we need to break 5 CH bonds. So what is CH bond? Is 412. So that's 5 times 412. What else do I need to break? I need to break a CC bond. So this is a thing very handy to have a highlighter, because you can just do this on the day. So that's going to be 348. I need to break 1 CO bond, because you want everything highlighted to be broken. That's going to be 360. And you want to break an OH bond, which is going to be, where the heck is it? 463. OH bond is 463. And we also want to break 3 moles of O2. So that's going to be 496. So 3 lots of O2s. Oops. I'm going to drop my calculator again, and I just did that. 496 times 2 times 3. And if we add up all these numbers, and that's going to be the total of bonds breaking. So let's add these up. So let's add all of these numbers up. So that's going to be 5 times 412 plus 348 plus 360 plus 463 plus 496 times 3. And that's going to give us 4719 kilojoules for the bonds breaking. For the bond making part, this one's a little bit confusing. Very easy to get this side wrong. Just look at the CO2 first. For every mole of CO2, I have 2 lots of COs. You have 1 CO on the left hand side, you have 1 CO on the right hand side. But then you have 2 lots of CO2s. So for every 1 mole of CO2, we have 2 CO bonds. But then because we have 2 moles, that's going to be 4 moles of C double bond O. So that will be 4 times where C double bond O, 743. Same with the OH bonds. You have 3 lots of H2O. For each single mole of H2O, you have 2 OH bonds. So that's going to be 2 times 3, which is 6 OH bonds. Hence 6 times 463. Add up these 2 numbers, which is going to be 4 times 4, 743 plus 6 times 463, and that's going to give us 5750. So this is going to be an easy subtraction. That's bonds breaking, that's bonds making. Take a difference, so it will be 4719 minus 5750 minus answer, and that gives us negative 1031 kilojoules per mole. And if I want to round to 3, SCF is negative 1030 kilojoules per mole. And if you're not familiar with rounding for 3 significant figures, start counting from the first non-zero number. So 1, 2, 3 round here. Okay, so if it's smaller than 4, smaller than 5, then that becomes a 0. Now do make sure you include the unit, because what are we calculating? We're calculating the enthalpy of change. The enthalpy of change has a unit of kilojoules per mole, as you can see with all the other bond enthalpies. Okay, so that's the first section. So let's just move on to organics. Yay! Now organic is a section that you either love it or you hate it. Okay, is going to be especially the flowchart stuff. The link to the notebook after one of the videos. I mean, my handwriting on the notebook is so messy, as you can see. So it's probably just just take a screenshot of the video. That's going to be easier. All right. So with the flowchart, I'm going to try my very best, and we're going to draw one together. Now the best way of doing flowcharts, I hate doing those alkanes to alkenes, alkenes to alkanes. You can memorize that like 50 times, and if I give you a flowchart, if you don't know how to use it, you still have zero idea how to do it. So my way of doing it with flowcharts is going to do it like this. Okay, so this might take into a lot of space, but I'm going to start with a really simple alkene. So we're going to do a lot of things here. We're going to name, and we are going to name these as well. And I'm not going to spend too much time on naming, but that's just achieved. So this is Butte 20. Okay, this is Butte 20, which is an alkene. Now, the thing with actually, you know what? Let's get rid of this, because I need all the space I can get. I'm going to do it up here. I'm going to need all the space I can get. Right, so this is Butte 20. Now, the thing with organic, you have to be smart about how to memorize these. Okay, when we look at organic, we always emphasize on the function group, because this is a part of the molecule that's going to react. If I react this thing with hydrogen/platinum, which is a catalyst, something has to happen to the alkenes. That's what alkenes always do. The double bonds always break. So when you break the double bond, can you see I'm just copying and pasting. I'm just copying and pasting. This is, you're gonna, if you do level 3 chem next year and come back to watch my videos, you're gonna hear me saying copy and pasting a lot, because the molecules become really complex on paper, but once you get the hang of it, you're literally just copying a really complex molecule, and then you are just changing the functional group. Okay, so I just copied it, but I break the double bond. What am I adding? I'm adding 2 H's. 1 H goes here, 1 H goes here. So that's an alkane right there. So this is butane. Okay, and what type of reaction is this? This is an addition reaction. So the only type of reaction that you alkanes will do is either addition reaction or oxidation reaction. So let's just do the addition reactions first. So next one. Actually, let's do it this way, because I'm going to use more space. If I add this, like say if I add Br2, what's going to happen? Same thing, like just copy paste, break the double bond, copy paste, and then what am I adding? I'm adding 2 Brs. The carbon is missing 1 Br, this carbon is missing, this carbon is missing bond, this carbon is missing bond. Just add them in. This is addition. And as you can see, we made a dibromo. So this is going to be, this is going to be 1,2-dibromo butane. Okay, now I'm going to move on to some of the harder stuff. If I add HBr, and this is where your excellence comes in. Okay, major minor products. Because if I do the same thinking, if I just copy paste, because the rest of the molecule doesn't matter, it's always going to be the double bonds. It's the functional group. Can you see I have a choice? I can either put the H here and I can put the Br here, and then I can do, I can do exactly the same thing. I can do exactly the same thing, but then I can reverse them. I can put the Br here and put the H here. So that's your two products. But which one's major, which one's minor? The major product, so this is where, and please, for the love of God, don't write major, don't write rich gets richer. That's not a chemistry rule. That's just a simple economics rule. I mean, it's true, but it doesn't. It's not a chemical concept. It's not a chemistry concept. It's simply we're just using something that everyone knows: rich gets richer, poor gets poorer, just to get you to remember it. But how we want you to explain it is that when you're doing addition reaction, when you're doing addition reaction, this is what we call an asymmetrical alkene because the double bonds on the first carbon. The first carbon and the second carbon, they have different number of hydrogens attached to them. The carbon number 1, I'm going to use carbon number 1 here. Let's pick a really obvious carbon number 1, carbon number 2, carbon number 3, carbon number 4. Carbon number 1 has 2 hydrogens attached, therefore it's more likely for that to pick up another hydrogen. That's your rich gets richer rule explained. Okay, so you can't just say, oh, it goes here, rich gets richer. Sorry, you won't get anything. Okay, but you need to say, because this carbon, like how I would tend to explain it, I'll label the carbons and I'll say, well, carbon number 1, carbon number 2 are double bonded, and then when the double bond breaks, carbon number 1 has more hydrogen, therefore it's more likely going to gain another hydrogen, and therefore you have a major product, and that's going to be called, what's this thing called? This is 2-bromobutane, and this is going to be the minor product, which is going to be 1-bromobutane. Okay, so that's, you know, this side of the reaction. What type of reaction is this? This is again an addition reaction. Addition reaction. Let me just get the oxidation reaction out of the way. If you react this guy with MnO2, now not MnO2, MnO4 minus, you produce MnO2 in that reaction. Now for some textbook it says MnO4 minus / H plus. I'm inclined to want you to just remember MnO4 minus. What's going to happen is that you still copy everything else, but this time you have to be really careful with the carbons at the end, is because you will make a diol. Okay, so this is oxidation reaction. You break the double bond. So the thing with the alkenes, you always break the double bond. Okay, so you break the double bond and make sure every single carbon has enough hydrogen. So this is a diol, what I just drew. This is a this is a diol, and that's called 1. This is butane. Butane 1,2 diol. Okay, so that's diol means 2 OHs. It's like dibromo. This is diol. Okay, so that's oxidation reaction. Right, so this is how your addition reaction. So if I do another one, if you didn't get the major minor products just now, let's do another one. If I add H2O / this is an important one, so I want to do this properly. Sometimes we say H2O / H plus. Sometimes we say dilute sulfuric acid. They mean the same thing. Okay, so don't get confused when they say dilute sulfuric acid and you freak out like, what? I never get taught this. My chem teacher sucks. You know, don't say that. These two are the same thing. Okay, they mean the same thing. It just means that the H plus is a sulfuric acid, H2O is a dilution part. Okay, now what's going to happen is exactly the same that compared to what we done just now, is that you again copy paste, and then you have a choice. You have a choice to make. In this case, same thing. I can put the H here and OH here, because what is water made of? Water is made of H and OH. And so these are your two products. And then same concept as what we just discussed over here. This is going to be major and this is going to be minor. Okay, why? Because this carbon already has more hydrogen bonded. It's more likely for that to going to pick up another hydrogen. And how do we name this? This is called butane 2O. This is called butane 1O. Okay, now we are going to struggle fitting everything in, but if I want to turn butane 1O back, if I want to make it go backwards, and remember when we went the other way, we used a dilute H2SO4, and on this side we're going to use concentrated H2SO4. So that initiates an elimination reaction. All of these are still addition reactions. These are all addition reactions. So when you go back to an alkene, you are making an elimination reaction. Let's say if I want to make the do I want to do it now? Well, I'll do it later. Yeah, I'll do that section a little bit later. So because I want to go back as well, let's do that a little bit later. Okay, so for addition reaction is you're breaking the double bonds. For elimination reaction, you're making the double bonds. Okay, now you can also do substitution reaction between these guys. Like say you got butane 1O, 1-bromobutane. I can actually convert the bromo. Why am I connecting the words? I can connect the bromo. I can turn this bromobutane, 1-bromobutane to butane 1O by using KOH aqueous, and that is simply substituting the Br with the OH. Okay, so this is a substitution reaction, because it's like if you play any sports, if a person gets tired, like say I used to coach football, if someone gets tired, like hey, sub, so I still get 11 players on the field. I just substituted someone that's not doing so well and putting someone else on. Okay, so that's substitution. Now, what if I want to, probably shouldn't use Br here. Let's say, how do I, if I do another substitution, what if I want to do, because bromine is not something in the course for this particular reaction. Like say if I want to, instead of going to Br, how would I turn that into Cl? This is where you would have learned PCl3, PCl5, or SOCl2. I will personally, again, don't write all three. I'll personally stick with SOCl2 because the other two sort of get stitched in year 13. We just go with SOCl2. And how do you remember this reaction? Being substitution, you substitute the OH with the Cl. And this is what I mean. If I give you this, and if I give you the reagent, you should be able to just look at that molecule. If you have a blank, every now and then I've done exam simulation, we all have moments like, oh, just blank out, you can't remember. Don't panic, just look at the organic function group. Just think what's going to happen to the function group. Nothing's going to happen to this carbon on the right hand side. It's not going to be that. It's always going to be the function group. So if you had SOCl2, and you would have learned absolutely nothing that had like sulfur and oxygen combined together added into the molecule. So it's not going to be that. Okay, so just common sense. Apply a bit of common sense. Now, the other part that I was going to do a little bit earlier is, so these are all substitution reactions. So as you can see, this flowchart is getting very, very messy. Let's make it even worse. So we can actually convert this guy backwards into the, to convert the haloalkane back into alkene using KOH alcohol. And sometimes they ask you the difference between KOH alcohol and KOH aqueous. And I always give this analogy. If you drink, like say, aqueous is to do with water, yeah? And it's important to drink water because that replaces your body fluid. So it's substituting your body fluid, and you get rid of the waste through, going to the bathroom. That's how you get rid of it. All right. Now, for KOH alcohol, if you get drunk, you lose stuff. And when you lose stuff, you will undergo elimination reaction. So you lose. What did you lose now? Because I don't have enough space, I'll do it underneath. What it means is that you lose the Br and then you form the double bond. So I will go at the look at the elimination reaction because I ran out of space over here. Okay, so elimination reaction, so pour gets pour. So I'll do that. Do I have some space? I have some space up here. Let's do elimination reaction. Let's expand this part a little bit. Okay, so if I want to turn CH2, sorry, the font change, some of you might get, to me, I'm not really picky with the colors, but some of you might want to use the same color. Go. Why is it not doing that? Go to that color. Why not letting me change? It's not letting me change colors. No, Wait, did I lock it by accident? Oh god. Alright. Oh no. Alright, let me just, don't you love OneNote? Alright. Yay. Let me do it. Okay, so if I want to go CH2 H, if I'm just copying pasting this molecule here, this molecule over here, CH2 CH3, like BR. Let's just rewrite it. I don't like writing CH2/H. That's just stupid. No one does that. Okay, CH3. Now, if I react with KOH alcohol, so remember we're talking about elimination reaction. We're talking about people getting drunk and then we lose stuff. So that means we lose a BR, guaranteed. You have to lose the functional group. And then you have a choice. If I number the carbons, this is 1, 2, 3, 4. So one of the H's of the neighboring carbon has to go. Because this carbon is losing the BR, and then you have to form a double bond either on the left hand side or the right hand side, and so you have to remove a hydrogen. So here we have a choice, so we can either, so again here we go, if I choose to lose this hydrogen on the left hand side, that will become CH2 double bond CH, CH2 CH3. So I've lost the H and Br, I've lost this hydrogen, and then that's why CH2. That's option number 1. And then I can choose to lose this hydrogen, so it'll be CH3. So I double bond on this side, and then you can determine which one's major, which one's minor by looking at the original molecule. So oops, if I look at the original molecule, the carbon number 3 has 2 hydrogens, carbon number 1 has 3 hydrogens, and this is where you ask yourself, okay, so we are losing stuff, we are losing things. So poor people tend to lose money easier, so poor gets poor. So that means carbon number 3, who is poor in hydrogen, is more likely going to lose another hydrogen. So therefore this one's major and this one's minor. And how do we name this? This is butene and this is butene. Okay, so that's just the elimination stuff, which is another excellent part. Right, now we're almost finishing with the flowchart. Now, another thing that you need to remember, this is a primary alcohol for the butanol. Sorry, I'm jumping spaces. Butanol, because butanol is a primary alcohol because the OH is bonding to a carbon which is only bonding to one other carbon directly. And this OH group is bonding to a carbon which is directly bonding to 2 other carbons. This is why this is a secondary alcohol. And you need to remember, guys, that your primary alcohol can be oxidized to a carboxylic acid. So if you didn't do so well for the redox internal, just remember that oxidation is gaining oxygens. Okay, so if you look at it before, I have CH2OH, so I only have 1 oxygen. You keep your OH, so that OH stays. You got rid of these 2 hydrogens, and then you gained the oxygen. And then that has to be double bonded because oxygen always bond twice, and that is your carboxylic acid. So how do we name carboxylic acid? This is always carbon number 1, number 2, number 3, number 4, because the carbon double bonded to this O and OH, single bond to the OH, is always carbon number 1. So this is butanoic acid. Now, just one last thing, you can something that I didn't do, which is amine. Can I do amine here? Yes, I can do it down here. I can convert, since I use that color, let's use this color again. You can convert, so you can put ammonia in the alcohol condition, and what that does, you are going to substitute, again, substitute the Cl with an NH2 group. Okay, so it's not NH3 because nitrogen only bonds 3 times. So NH3 here, you can see this nitrogen is bonding 3 times, but this nitrogen is also bonding 3 times because it's one of them is bonding to the C, one is bonding to the C, the other 2 is bonding to the hydrogen. Okay, so that's this is again a substitution reaction, and this is oxidation for the one that we just talked about. Okay, and butanoic acid does one more thing. If I react this with sodium hydroxide, and this is going to be a neutralization reaction or acid and base reaction from year 11. But remember, how do we determine something is an acid? They will lose the H plus ion, because that's what all acids do, and then it will be COO. Everything else is kept the same, but that will become COO minus because you lost the H plus, and then you should technically combine this with the Na plus sign, so that should be written as COONA, and then the rest of the molecule. So this is called sodium not ethanoate, butanoate. And this is the part that people get really confused. Like they go, what the heck is a butanoate? Butanoate is just when you have butanoic acid, you lose the H, that becomes a butanoate ion. It's like sulfuric acid. When you lose the H, it becomes sulfate ion. Like nitric acid becomes nitrate ions. Butanoic acid lose the H, becomes butanoate ions. Okay, and the sodium is just a sodium part. Now there are some parts of the flowchart that I probably would have missed, but this is I mean, this is how you can revise. You can literally, if you want to make yourself a little bit challenge yourself, start with the molecule like I did. Start with an alkene. Don't make it like a 6 carbon 7 carbon alkene. Just start with something simple. Maybe you can try like something like methylpropane, or 2-methyl butane. You know, you can make it challenging a little bit, and then you can try to do what I did, because if you can do this, you will ace that flowchart. Okay, you can do really well for the flowchart in if you can do something like this. All right, so that's the flowchart. So don't spend time just go, I need to memorize, but you need to know how to use it. It's like if you don't know the flowchart, you definitely won't do well in organic. But sometimes if you memorize the flowchart, but if you don't know how to use it, then you still won't do well in organic. Okay, and especially if you continue, if you're thinking about continuing in year 13 chemistry, you need to do well in organic, because you have a fire critics external, which is obviously organic, continuing in year level 3, and a lot of the merit questions are from year level 2, and also the thingamajiggy, what do you call it, the spectroscopy internal, which is also based on a lot of organic chemistry stuff. So it is something that you really need to spend a lot of time on. All right, isomers, we're going behind on time. So C5H2, so this is an isomer. So what it means is that this is a structure, so we can do some structural isomers. So I'm just going to draw, let me draw all of them, why not? All right, so I can tell this is an alkene because the hydrogen number doubles the carbon numbers. Okay, so I can make structural isomers. So structural isomers is when they have different, they have the same atoms bonded, same type of atoms, same number of atoms, but then they're bonded differently. So I can draw many different things. Okay, so I can draw this one. This is pentwaning. I can draw this one. This is pentooing. I can draw, so I've run out of carbons in the 5 carbon chain. I can do 2-methyl pentwaning. I can do 3-methyl pentwaning. I can do, so I've done the, and then you just move the carbons around, move the double bond around, and I can do 2-methyl butooing, and I can, is there any more? No, that's all I can do. Okay, so if that's 5 different isomers. And as you can see, I could even do the H's, and I just do the H's after. It will be a lot easier to do this afterwards. Okay, so I'm not gonna, should I bother with the rest? No, I won't bother with the rest. Okay, so, and then the next part, so this is quite important. The next part is, how do you get geometric isomers? So geometric isomers are your cis and trans isomers. So there are 2 conditions you must have. First, you have to have a CC double bond, which prevents rotations around it. The second thing is that each atom, the two groups bonding to each carbon in CC double bond must be different. Okay, so that means straight away this one can't have geometric isomers, can't have geometric isomers. Why? Because this carbon we look at the double bonds. We look at that. We look at that. We look at that. We don't care about the other things. Can you see that's two H's straight away? That can't have geometric isomer because it doesn't satisfy that criteria. So same thing here. So that CH2 doesn't satisfy that criteria. And then this carbon here, you might think that may have geometric isomers, but then if you look at those two CH3s, they are the same groups bonding to this carbon in the double bond, so they can't have geometric isomers. So the only possibilities. Actually, this one's rubbish as well because that has a CH2, so that's wrong as well. So the only possibility is this guy. And we can redraw this, so we can, let's draw the cis and trans isomers. So put the double bond in the middle, centralize it, and just copy paste whatever you see. Can you see this carbon, this hydrogen is this hydrogen, and then I have CH2 bonded to CH3. And then on this side, I can have H on the top and then CH3. The two H's are on the same side, so this is cis. And then I can just flip one of them around, like I just did that. Don't flip both sides, because if you did that, then you just draw the same structure 3 times. Again, the H's are on the opposite side, so this is the trans structure. So this is an excellence question as well. Pretty straightforward to do. And yeah. Next part, distinguishing tests. Distinguishing tests. So we're a little bit running behind a little bit. So bromine water is really useful to tell alkenes and alkanes apart. It's really useless for everything else. For alkene, it goes from orange to colorless straight away. For alkanes, you need UV light to act as a catalyst, but then you will do orange to colorless in a few minutes. I say in 5 minutes. Okay, so that's how you can tell if you have alkenes or alkanes. Just chuck them in bromine water. The one that will go from orange to colorless straight away is the alkene. The one that does it in a little bit with UV light is alkane. Litmus paper. Litmus paper is really useful for carboxylic acid and amines. Amines are basic, so they will turn litmus paper blue. And carboxylic acid are acidic, from the name acidic, so they will turn it red. Okay, very straightforward. Now for these two, they would be really helpful to distinguish primary alcohol, because primary alcohol can be oxidized into a carboxylic acid, and that will see a color change. So this is going from orange to green, and then your purple potassium permanganate, the triple P's I like to call, goes from purple to colorless. Okay, so this is really useful to distinguish primary alcohols. And then you may have MnO4 minus. This is really useful to distinguish alkene again. But sometimes, because if they let you choose what thing to use, then I'll use bromine water any time of the day. This will react your alkene to a diol, and that will go from a color of purple to brown. Okay, so this is useful to distinguish alkene, because they may go, you have to use this to distinguish alkene. You can't use bromine water, and then you have to do this, and you have to know the color changes. And in water, this is to test for solubility. So if you mix the following things with water, you get one layer. So that's your short chain alcohols and your carboxylic acid, your amines, because these things tend to be polar. And then 2 layers, your hydrocarbons, so your alkanes, alkynes, alkenes, everything to do with hydrocarbons, they all don't dissolve, so you get 2 layers. Your short chain haloalkane kind of will dissolve as well. Haloalkane will dissolve, only short chain ones. So hydrocarbons don't dissolve. And are there any other functional groups that you learn? Nope, that's it. Okay, so if you get 2 layers, that's normally when you have an alkenes. Think of petrol. Petrol is a hydrocarbon, like it doesn't dissolve in water. All right. Now, I do believe I'm not even going to bother with polymerization, because additional polymerization is going to be an achieved question. So, oh, really? Someone said do additional polymerization. Okay, I'll do that for you, buddy. Since I just read chat, and then I see, can you do addition polarization. I'll do it for you. All right, let's pick a monomer. Let's pick this one. Just make a really simple one. All right, so this is a monomer. What are polymerization reactions? Because when you do level 3, polymerization becomes the most difficult part. That's excellence. And at level 1, at level 2 chem, that's only achieved. Okay, so what that is, that's monomers. So if they ask you to draw 2 repeating units of the monomer, this is something I ask my guys to do. You know, one, they just learned it, is to just copy paste again. Can you see I'm just drawing them one up, one down, one up, one down. I'm just putting them right next to each other. So as you can see, this is 2 units. Okay, so how we did what the next thing is, remember alkenes always break the double bonds. So I've broken the double bonds and I join this together, and I simply will join to something else again on the other side, join to the other thing on the right hand side, and this is your polymer. Okay, so that's for you, 2 minutes of additional polymerization for a simple achieved. And then if we want to go backwards, how do you figure out what monomer that you should have? Can you see this thing here and this thing here is being repeated? So what you do is that you draw a line in between and you copy that. So you just you know, Control C, Control V, and then you complete it with the double bond, and that's that done. Okay. Last question, last section. 2.6 chemical reactivity. So this is going to be hopefully the easiest one to do, because rates reaction you did in level 1, and no one fails chemical rates reaction part in level 2 because you did it in level 1. The Chatelier's principle is probably gonna get a lot of people confused, and then S as a basis pH calculation. I mean, if you're someone, I'm not trying to discourage you from taking chemistry in level 3. If you're finding pH calculation difficult at level 2, I would strongly advise you to think twice about taking level 3 chem, because 2.6, when it becomes 3.6, it becomes 95% calculation. If you find 2.6 calculation difficult, then if you don't really need chem for your future career, take something else, okay? Because otherwise it's not going to be a very endurable 6-7 weeks for you, because it's all calculations. So let's get started. All right, so rates reaction, I'm not going to spend too much time on this. Like I said, all year 11 stuff. Rates reaction diagram, something like that, you know, at the beginning, lots of chemical reactants, lots of pollution per unit time, blah blah blah, same, you know, the same crap that you always get in year 11 science. I'm sure you get tired of hearing that again. The key thing is that we always talk about is temperature, because temperature, when you increase temperature, you have more kinetic energy. When you have more kinetic energy, the particles move around more. When they move around more, they're more likely to collide. And once they do collide, a higher proportion of these collisions will have sufficient amount of energy to overcome the activation energy, and that will results in a successful collision. Therefore, the number of successful collision per unit time would increase, hence higher rate of reaction. Okay, so if I'm going too fast, just go back to my other videos and just, you know, because every year this is the same question. I get really tired of doing it. But do become very careful when you talk about things colliding with enough force. We do not accept force at year 12. Year 12 chemists now, we only accept the word of energy. Okay, so you must collide with sufficient amount of force. They must collide with sufficient amount of energy to overcome the activation energy. It's like, don't think of elephant, don't think of elephant, and then what do you think about? You think about an elephant. So just that's what happened there. Surface area and concentration, I don't even think they get asked that much. Catalyst is actually quite interesting. So if you have, let's say, an exothermic reaction here, a catalyst is something that provides an alternative pathway which lowers the activation energy. So what that means is that when something that used to collide and didn't count as a successful collision now would have sufficient amount of energy, because the activation energy has been lowered. Okay, so this section, I'm not going to spend too much time on this because it's been repeated so many times. It's something like, if you're being smart about it, I would highly recommend you to just go watch those 2 videos, just grind it out. It's actually really easy to get merits and excellence for this first question. Okay, Le Chatelier's principle. Let me just take a sip of water, because this is going to be the interesting part, especially in our own school exams. This is by far the worst attempted section, which is understandable, because the what do you call it, if you can't get your head around the whole equilibrium thing, it becomes quite difficult, but once you understand it, it's actually quite easy. All right, so let's have a look at this. I'm not going to bother reading that paragraph there. So here's the equilibrium. So writing the Kc is the ratio between the products and the reactants. So products goes on top, so that becomes N2, the concentration of N2 times the concentration of O2 divided by the concentration of NO to the power of 2. Why is it to the power of 2? Because that coefficient of 2 becomes the square. Okay, now not plus, please. For a lot of our schools kids, don't write plus. You get wrong straight away. Now next part, we are going to calculate. So the value of Kc is 2500. Calculate the concentration of N2 in the equilibrium mixture if the concentration of O2 is this and the other one's this. So all you need to do, Kc equals 2500. Substitute numbers in. N2, I don't know, times O2, which is 0.422 divided by 0.00751 squared, and you should get a final answer. I'm just going to quickly do this on my calculator, and I was saying this to Mr. Infinity Plus One the other day. I was like, you know, it really triggers me how if I give you this equation, a lot of people just go, what? How do I solve this? How do I make this a subject? And I was even mentioning this in another video, and he commented on it because I just say, I literally just said, if you don't know how to do this, go to his go to him, because he's a math teacher. He should be able to help you a little bit more than I can. Okay, so your final answer should be 0.334 moles per liter. Let me just do the calculation again. I don't want to look like an idiot when you do this calculation on your own and then get a different answer. Yep, okay. Now, when you're doing this, do not delete numbers from your calculator. Use the whole thing. Okay. Don't delete the numbers halfway through. You can round it, but then don't delete it. Use the whole thing. All right, next one. All right, equilibrium. Okay, so this is an equilibrium. Delta H is negative. Ammonia gas is added to equilibrium mixture at constant temperature. So constant temperature. Circle the statement that best describes the value of Kc. Is constant temperature, it will stay the same. Kc only changes if temperature changes. Okay, so just remember that. So that's all I'm going to do. Next one. The H2O produced... Oh, I still need that. Damn. I still need the equilibrium. The H2O produced in this reaction is removed from the equilibrium mixture. Circle the statement best describe the change in the amount of nitrogen. Okay, so when you have the equilibrium like that, when you decrease, what do? The H2O produced in the things removed. Okay, so we're removing the H2O. So that thing that I've just circled is being removed. So that means the system is no longer at equilibrium because your Kc has changed. It's no longer at equilibrium. So what's going to happen is that the system will try to reverse it. They'll try to minimize the change. And how do they minimize the change? They are going to favor the forward reaction to make more H2O. And when they so the forward reaction is going to be favored, and in the process of favoring the forward reaction, the concentration of N2, in this case that's what they're asking, is going to increase, because while you're making H2O, the N2 concentration would also increase. And now I'm just going to do a little bit extra. The NH3, the things on the left hand side, and the O2 concentration, these two concentrations will decrease because they are being used to make the extra H2O. But then once the system has re-established equilibrium, the Kc value will still be the same, okay, because the ratio doesn't change. Next part, the amount of nitrogen formed can be altered either by changing the temperature or the pressure. Evaluate the changes that can be made to both temperature and pressure to increase the amount of nitrogen produced using the equilibrium. So what I'm going to do, I'm going to just copy paste this equilibrium down so we can just recycle this underneath because I need more space. So the best way to read, I mean, like I said, I only have an hour and a half, and I'm definitely not keen to do more past 11 because my brain just shuts down after 11. It's really important that I mean, you had 6 weeks to 7 weeks per topic, and I'm doing this in 1.5 hours for 3 topics. So there are a lot of things that I'm probably not covering, but I'm just covering the important things. So just, yeah. If you want more detailed explanations, go watch my other videos. All right, and subscribe if you haven't, by the way. All right, so let's have a look. So let's go with the easy part. Let's go with pressure. How do we? So they're saying, how can we make more N2? So if you look at pressure, pressure is dependent on the number of gas particles. So when we want to make more N2, so that means we want to make the reaction, we want to make the system shift to the right, yeah, because you want to make more N2 to the right to make more N2. That's the goal. So how can we make it go right when we're dealing with pressure? So pressure is to do with the gas of particles. So we have 7 moles of gas particles on the left, 3 plus 4. On the right hand side, we have 8 moles of gas. So how can we, you know, make it shift that way? So this is where you will need to decrease pressure. So pressure needs to be decreased. So pressure should be decreased. Why? Because when we decrease pressure, that's going to favor the side with more moles of gas particles to minimize the change. Okay, to minimize the change of this decreasing pressure. So therefore, in the process, we'll shift to the right to make more N2s, and that's how we're going to do this. Now, changing temperature. So we want the reaction to favor N2 again. So the forward reaction is negative, hence is exothermic. So how do we make the reaction favor a forward reaction? Well, how do we make the reaction favor an exothermic reaction? This is when you must decrease the temperature. Decrease the temperature. Because when you decrease the temperature of the surrounding environment, then the system wants to minimize the change. So it's like, think about, oh, the room is getting colder. How can I minimize that? By releasing some of the energy. So you have to favor the exothermic reaction, and as a result, the N2 concentration would go up. So the equilibrium section is more of a, just try to get your head around it. And once you do, then it's, yeah, not too bad. Just remember like I said before, just remember one thing. Just remember, okay, if I increase pressure, I favor the side with less moles of gas particles. If I decrease pressure, then favor the side with more gas particles. Just remember one of those two, because the other one's the opposite. Temperature, if temperature increases, I favor endothermic to suck in all the energy. Or you can remember as if I decrease the temperature, then the system needs to release some energy to make up for the energy loss. Hence, I favor the exothermic reaction. Remember one of them, the other one's the opposite. Next one, so this is the hardest equilibrium question. This one is the one I do want to make this, you know, this type of question is the most difficult, okay? So here's the equilibrium, and I'm gonna make this excellence question look really easy. I hope, especially if you haven't seen my other videos. So as you can see, let's just write down the obvious. What happened? As temperature increased, my Kc increased. Okay, so let's just write that down. Temperature increases. As temperature increases, Kc increases. Okay, so that's anyone, you know, that can read should be able to see that. Yeah, temperature has gone from 25 to 300, Kc increases, and then Kc has gone up from 10 to the power negative 4 to 10 to the power 2. So that's obviously gone down. Gone up. Okay, so temperature increases, Kc increases. So what do these two sections mean? Temperature increases. Let's go back to the thing that we just talked about. If you increase the temperature, which reaction is going to favor? Which reaction is going to favor? Which is it going to favor, the endothermic reaction or the exothermic reaction? So just remember, if you increase temperature, that means the surrounding environment gets too much energy. So how does the system minimize the change? By sucking in some of the energy. Okay, so endothermic reaction is favored. All right, Sorry, someone just sending me a text on their phone. What's she saying? Oh, never mind. All right, so the endothermic reaction. So endothermic reaction is favored to absorb the extra heat energy. Okay, so remember that. Because what is the question asking us to do? We're trying to determine whether the formation of the thing is endothermic or exothermic. Okay, so we know temperature increases, we favor endo. Okay, now let's look at the other side. Kc increases. Kc increases. So remember, Kc is a ratio between products divided by reactants. If Kc has gone up, doesn't that mean there are more products? Yeah, that should be really obvious. There are more products, less reactants. Otherwise, how are you going to get a fraction to go up? This is the only possibility. Now, if that means you have more products and less reactant, doesn't that mean the forward reaction has been favored? Forward reaction is favored. So we know that the forward reaction is favored. We know for when the temperature increases, the endothermic reaction must be favored. Therefore, the forward reaction is endothermic. This question is done, and that's your excellence. Okay, and yep, that's that part. That's all the enthalpies, not enthalpy, all the equilibrium things that I'll talk about. So hopefully that makes sense. I see you guys talking about Kevin. Kevin is very, very intelligent, being level 2 and doing level 3 stuff. Yeah. All right, so let's do the last part, which is the acids and bases. Okay. So again, these questions don't they aren't from old exams, so just make sure that we can you understand the concept. So acids and bases. So acids always donate. Like if I do this, just to show you one reaction. When HCN acid an acid, it donates the H to the water, so that becomes H3O plus, and then the HCN lost in protons, so that becomes Cn minus. So Cn minus is a conjugate base. The acid for NH3 is NH4 plus, and for NO2 is going to be HNO2. So the thing that you need to remember that your acid and base, your acid and conjugate base should always be one. Should always be one. What do you call it? Blah 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 blah. 1 H plus difference. Okay, so the hydrogen carbonate ion. So this part as an acid. So this is the amphil product idea, something that can act as an acid base. So in this case, HCO3 minus as an acid will donate the H to that, so it becomes CO3 2 minus plus H3O plus. And then when it's acting as a base, so the H2O gives away the H, so it becomes H2CO3 plus OH minus. Okay, now calculations. A solution of acid has pH of 1.25. Calculate the concentration of that and the concentration of the hydroxide ion. So just remember the two equations. The H3O plus ions is 10 to the power of negative pH, and then pH equals negative log H3O plus ions, and then we know that OH minus times KH3O plus, which equals to KW, which is 1. Oops, that's an ugliest W you ever see. KW, which is 1 times 10 to the power of negative 14. So if you can, let's say pH equals 1.25, so straight away we know 10 to the power of negative pH, which is going to give us H3O plus ions. And then if you do that on your calculator, which is 10 to the power of negative 1.25, that's going to be 10 to the power of negative 1.25. That will be 0.0562. That's H3O plus ions. Okay, now to figure out OH minus ions, you just use 1 times 10 to the power negative 14 divided by the whole thing that we just did, not just this number that I'm writing down. You should divide by the whole thing, divided by bracket answer, and then you should get 1.78 times 10 to the power of negative 13. Remember the units. moles per liter. Okay, now calculate the pH of 0.205 mole solution of base potassium hydroxide. So when you get a base calculation, there are two ways of doing this. So we know the OH minus concentration is 0.205. So what you can do is you can use this KW thing to find out the H3O plus concentration, and then you just go pH equals negative log H3O plus, and that gives you the answer. I personally hate that method because that's too many calculations to do. The thing with people doing science is that we want to make our life as easy as possible. Okay, so yeah, let's do the easier method. Now you know how pH. So I'm gonna use this equation here. You know how pH is negative log H3O plus. pH is just a scale that we come up with for the general public to use. We can play, it's just potential of hydronium. I can do potential of hydroxide. It's just that if I negative log OH minus, that's POH. So if I do that, POH equals negative log OH minus, and then you can see that OH minus equals 10 to the power negative POH. So this is just using mathematics just to make our life a little bit easier. So what I can do negative log 0.205, and that will give me a POH. So that will be negative log. So if you've never seen this method before, don't panic. Don't be like, my chemistry teacher never taught me this. Don't panic. It will give you 0.688. This is a POH. The pH and POH add up to 14. Because of the KW, which is 1 times 10 to the power negative 14. So if you use 14 minus 0.688, you get 13.3, which is going to be the pH. There you go. Nice, easy, much easier method because it takes less calculation steps. The more numbers you put in your calculator, the more likely you're going to make a mistake. Oh my god, all these things to do. All right, so the following table shows the concentration and electrical conductivity of 3 aqueous solutions. So this is a strong acid, strong base, weak acid. Okay, because I can tell from you can see the concentration all the same, but this is a good conductor, this is a good conductor, this is a crappy conductor. Okay, so how do we write the equation? Plus H2O, this is going to completely dissociate and then give us a lot of free moving ions. That's why it's a good conductor. But then for the CH3COOH, it is a weak acid. So when you react with the water, only about 1 to 5% of it will partially dissociate, and then you get the, oh my god, come on, OneNote. I think I asked you to rewrite that. All right, COO minus plus H3O plus. Okay, so NaOH. I don't tend to include water in there because it doesn't really do much. You just literally just separate that into Na plus and OH minus. Okay, so why are these good conductors? Because these guys that I just ticked are good conductors because you have lots of free moving ions because they completely dissociate. And whereas the weak acid only partially dissociates, so you only have a very small amount of the free moving ions. Next one. So you got given some pH values, we're going to assign them. So HCl is a strong acid, that will be 1.00, NaOH is a strong base, so 13.0, and then 2.88 obviously for the weak acid. Give reason for your answering relating to the pH value, to the strength and relative. Oh my god, it's another question down there, so we're going to run past 11 o'clock test. Okay, give a reason relating to assigned pH value to strength and relative H3O plus solutions. So this is very similar to what we just did just now. We can, they say no calculations unnecessary, so you don't have to calculate. So it just means that the HCl will completely dissociate using the same equations that we just talked about. That means we'll produce a lot of the H3O plus ions, and that the more H plus ions you have, let's just do this. So HCl completely dissociate. I'm just gonna explain one. Completely dissociate. Okay, so that means lots of H3O plus ions. That means low pH. The more of this you have, the lower the pH. Vice versa, NaOH completely dissociate, lots of OH minus, therefore really high pH. CH3COH, let's do CH3COH. It partially dissociate, so you will still generate some, you still make some a hydronium ion, but then obviously not in a huge quantity, therefore the pH is going to be, you know, meh, 2.88. Is this the last one? Yes, it is the last question. All right. The table is a repeat of the table from the compare the electrical conductivity. So I kind of did that, didn't I? The particle respond. I think we're going to finish at 11 o'clock. I just talked about it just now. So the particle responsible for the electrical conductivity, obviously the free moving ions, the more they dissolve, the more they dissociate, the more they will be able to conduct electricity. Okay, so I do want to talk about one thing though. Let's say if I give you CH3COO and A, this is where people really get thrown off. And this probably has a pH of, let's say, 8.51, for example. I'm just made it up. And then people don't understand, why does it have a pH of 8.51? So you need to be able to break that down into two steps. The CH3COO and A, first of all, it will dissolve in water, and that splits off into the CH3COO minus and Na plus. Okay, so this is the same thing as what we did before. So it's like, this is a salt and you're dissolving it. So when you dissolve it, you will produce the two ions. And then what's going to happen next is that the CH3COO minus, because you're dissolving this in water, you will do something with the water, will partially dissociate in water, it's going to pick up a hydrogen from the water molecules, and then it's going to become CH3COH and OH minus. So because you're producing some OH minus, this is why it is going to be a weak base. This is what we call an alkaline salt. Because it's not a neutral salt. What is a neutral salt? A neutral salt is NaCl. Like, this is a prime example of a neutral salt, because what does that do is splits off into Na plus and Cl minus ions, but neither of these ions will react with water. So they will just sit in water and do absolutely nothing. But then the CH3CO minus that we just produced will partially dissociate and form the conjugate acid. Okay, so that's a really important one that I'd like to point out, because that wasn't included in this particular section. All right, so there it is, 11 o'clock, and Tanish just joined. So the video will be available. Like I said, I don't want to do this the night before the exams, because I want to give you a bit of space and a bit of time to go through this again tomorrow, have a look at the videos before, and so yeah, so this, I probably won't be doing any more year 12 content. I'll probably spend the next 2 days for the year 13s, who probably needs a little bit more attention. So yeah, all the best with the exams. If you do have any questions regarding any year 12 contents, like with the videos and stuff, just leave a comment underneath. I normally respond within like at least no more than 2 hours. I do respond. I do check my notification quite frequently. So all the best with your exams, and yeah, and I'll answer your queries. So, and if you do decide to do level 3 chemistry again next year, you can always come back here for some more tutorials. Okay, so all the best, and I'll see you guys